Hello everyone and welcome to another video. Today I'd like to expand on some of our previous discussions where we talked about how to transform a vector using rotation matrices. So in these previous discussions we showed how you can use a rotation matrix to express a vector in different frames. If you haven't seen this first video discussing expressing vectors in different frames using rotation matrices, please make sure you watch this first, as these ideas are going to be critical for the discussion today. Also, it wouldn't hurt to review the other video talking about Euler angles, as this may also help comprehension of today's topic. So one thing that was implicit to these previous operations / rotations was that the origin of those two frames needed to be coincident in order to perform the transformation. And obviously this isn't always the case. You know, for example, you might have a coordinate system set up at a launch point of some vehicle, and then another coordinate system or frame attached to the body of this space vehicle, which is obviously translated and rotated away from the launch point coordinate frame. So this is kind of interesting and provides a little bit of a discrepancy to our previous discussions. So today I want to talk about extending the idea of the rotation matrix to take into account both the rotation and the translation simultaneously. So if this sounds like more fun than a box full of bubble wrap, let's jump over the board and get started. All right, so to start this discussion, let's just begin with a pretty standard frame. And you'll see actually I've drawn this very nicely with a nice straight edge. That's going to be important later. I'll show you why. But let's call this first frame, how about FR? So let's make this like our quote-unquote reference frame. And let's just make this your standard, how about east, north, up frame. So in other words, the x-axis, let's call this XR. This is like east position. Okay, and then YR is in this direction, YR. This is sort of like your position north, how far north you are. And then obviously Z is then coming out of the page, right? So you got ZR, which is the up direction. So again, think about this as just like a planar situation where you got east running this way, north going that way, and up coming out of the board. We're going to stick to a planar two-dimensional case for the majority of the analysis, but all of this will readily extend to 3D as we'll discuss a little bit later. So anyway, this is frame FR. Okay, so nothing fancy yet. And this is pretty much our discussion that we had earlier. Let's say that you've got some target or something like that, or like a, I don't know, or a position of interest, like some pedestrian. Let's say, maybe I should not use the word target because that's probably the wrong thing to think about. But let's just label him as T, as this point of interest, which is the center of this person, right? So right now, it is pretty easy to go ahead and measure or to discuss what is the vector which goes from the origin of frame R to the point T, okay? So maybe, again, I want to make sure I draw this very clearly. So let's get a ruler, our straight edge, okay? And I want to do something like this. Let's call this here. Well, geez, man. Should just draw the vector first and then make the guy line up with it, but okay, so this green line there, right? We can call this green vector, right? This is the position of T with respect to R, okay? And I'll put a vector mark on top of that, right? So this green line is the position of point T with respect to the origin of frame FR, right? Nothing fancy here, okay? Now, let's say that maybe we are looking at like a, I don't know, like a self-driving car or some kind of situation like that where you've got a car or some vehicle, okay? The vehicle can be sitting right here, okay? And the vehicle has its own body frame, which may not be aligned with the east, north, up, right? I mean, you can point your car any direction. You can be driving anywhere in this plane. It can be pointed, you know, this way or that way, or, you know, completely backwards. So we need to stick a body frame attached to this car, right? So let's go ahead and I'll grab my little prop I've got here. So we're going to stick an X body frame, which is aligned with the vehicle, right, pointing out the nose. The Y is then coming, in this case, is going to come out the left door. And then I guess the Z axis of this body frame is coming out the roof of the car. So let's just arbitrarily attach this, well, I guess not arbitrarily, but let's attach this body frame to the vehicle like this. All right, does that make sense? Okay. So now you can also ask, what is this vector RT with respect to R or RT with respect to body. Since their origins are the same, it doesn't matter, right? The only thing that differs is this rotation matrix, which is going to measure the angle between the reference frame and the body frame, right? And this is the exact picture that we had in our previous discussion when we were looking at expressing vectors in different frames using coordinate rotation, using rotation matrices, right? As long as the origins of frame FR and FB, maybe we should write that down up here. Let's write our FB on the very top, okay? So let's write FB here is our standard body frame, right? So X is out nose of car, or out front of car, and the Y body, I guess we should say like this, is out the left side of the car, okay? So as long as this was the case, I could express this green vector either in the reference frame R, or I could express it in the body frame B, and the only difference is a rotation matrix between the two, right? Okay, now here's where it gets interesting. Again, let's think about this from a self-driving car perspective. Let's say that this reference frame, like this is your base of operations, and you're going to drive this car and deploy this self-driving car from the base of operations, okay? So this thing is going to be driving along, doing whatever, right? So its body frame is moving, doing all this other kind of stuff, and let's say it ends up, I don't know, like something like this, okay? Let's say you're sitting like, I don't know, let's make it something like that. Okay? Now, this car is displaced or translated from the origin of FR, right? So the origins of these two frames, of the body frame and the reference frames, they are no longer coincident, right? So we can now talk about what is the vector from the origin of the body frame with respect to the origin of the reference. So what we can do is let's go ahead and draw that vector right now. Okay, so I can draw a vector. Again, I'm trying to get a straight edge that is the right length. Where did I put my straight edge? This is, oh, here it is. Okay, let's use another color for this vector. Okay, so I'm going to draw a vector from, okay, like this. Ah, shucks, I have a hard time holding this thing straight. This whiteboard is surprisingly slippery. Okay, there we go. Okay, so this is going to be the position vector. Let's call this RB with respect to R, right? So that's the position vector of the origin of the body frame with respect to the origin of the reference frame. And I guess maybe we should make it kind of something like that, right? Because it's all the way to the origin right up there. I think you get the picture I'm trying to draw, okay? Now, here's what's interesting. Now, let's say that the vehicle, right, this is a self-driving car, it probably has things like LiDAR, echolocation, vision system sensors, all that kind of stuff. It can measure and it can sense obstacles in the environment like this pedestrian, right? So what we could think about is, what is the position vector from the car to the pedestrian with respect to itself, right? Because the car is going to be able to sense where is that pedestrian with respect to itself. So in other words, what I want to draw now is I want to draw another vector which goes from the origin of the car. Maybe I better, let me take this off for a second, just so we can make sure that everything looks appropriate, like this, right? So now we have another vector like that, okay? This is the position vector of the target or the pedestrian or point T with respect to the body frame, right? Okay? And again, the picture that goes on top of this is I got to put the car, I guess, kind of like that, right? Okay, so now this is getting interesting, okay? Because if you think about this, what we can do now is we can say that you have the car is able to measure this vector, right? It's able to sense the pedestrian with respect to itself. But the question now is, what is the position of the target or the pedestrian with respect to the base of where it left, right? From where the car left, okay? So we want to be able to see, can I compute this green vector given these two red vectors, right? So let's write that down. So what we want here is, if you think about this long enough, I want to get the position of the pedestrian with respect to the origin of the reference frame, right? From where we left, and I want this thing expressed in the R frame. I want to know, here's where the car left. Okay, how far east is the pedestrian and how far north is the pedestrian from the base of the origin, okay? And now what you're given, right, is we are given our position of the pedestrian with respect to the body of the car, but expressed in the body frame, right? So this is measured by the car, by the self-driving car, you know, maybe via camera sensors, camera, LiDAR, you know, whatever range sensors and kind of processing algorithms the car has on board, it sees the pedestrian a little ways in front and to the right of it, and it can measure how far that is. So it can make this measurement of RT with respect to B, okay? We also are given RB with respect to R, okay? This is going to be expressed in the reference frame, right? So again, if you think about what this is where the car is located, how far east and how far north is the car with respect to the base. So this is something, you know, measured, I don't know, by GPS maybe or something like that. Let's say that, measured by, I don't know, GPS, right? GPS will tell you how far away you are from a given point in terms of X, Y, okay? And then lastly, the last thing that we will also need to know is we need to know this angle psi, right? Which is the rotation angle between FR and FB. Okay, so maybe what we should do is let's draw that on our picture here. Okay, and this angle, right, is if you look at it long enough, let me go ahead and draw one more sort of small intermediate frame. So I'm gonna pop the vehicle off for a second. Okay, and I guess maybe what we should do is we should maybe very quickly, let me draw where the body, I don't have a purple, but I guess you're gonna have to remember this is supposed to be purple. Like this is where the X body axis was pointing. Here's X of the body frame, and then 90 degrees to that should be, this should be Y of the body frame, right? Because this was the car sitting right here, and I just want to pull off this car because this car graphic takes up a lot of space. Okay, so now what we can also do is let's define an intermediate frame F1, which is the same thing as FR, but just has its origin aligned at the same point as the body. So in other words, what I'm going to do here is I'm going to just translate this. Maybe I should do it in black, the same color that the reference frame was in. Let's do it like such. Okay, so then you see here we get this here. Yep, here is, let's call this X of the one frame, and then 90 degrees to that is Y of the one frame, okay? So the one frame, shucks, I ran out of room right here. Maybe let's write it down here. So this F1 frame is intermediate frame that is aligned with FR, but with origin at FB origin. And again, this is, I'm using the word frame loosely. I think some people, if you want to be really technical, they define a frame as just the directions and then a coordinate system as a frame with an origin. So I guess technically here, we're really talking about coordinate systems because I do care about where the origin is, whereas previously when we were just doing rotation matrices only, we only cared about the frame. But for most intents and purposes, those two are kind of interchangeable, a frame and a coordinate system. So, okay, does this all line up? This all makes sense? Okay, so then the angle psi that I'm looking for is really, it's you can almost think of it as the Euler angle, right? It's the yaw Euler angle between the body frame and the reference frame here, right? So here's where psi is, okay? So if we're given all of those, can we make that calculation, okay? All right, so yeah, I think we can get started. So what I want to do then to get started with this, we've got all the relevant geometry up on the board there. So the first thing we're going to do is let's go like with the step 1 here. Let's calculate this intermediate parameter. So let's calculate, what I want to get is RT with respect to B, but expressed in the 1 frame, okay? So this is the position of the pedestrian with respect to the car expressed in the 1 frame, not in the body frame, right? We already have this right here. Okay, but I want to rotate it to the body frame. So this is actually pretty simple, right? If you think about this, so RT with respect to B expressed in the 1 frame. Well, I already have the position of the pedestrian with respect to the car expressed in the body frame, right? This was what the car knows by itself. It measured via LiDAR or camera sensors or whatnot. And now, if you look at this picture, this, if you ignore all this junk down here, right, and all you focus on is just the 1 and the body frame right here, this is the exact picture we were looking at when we were talking about expressing vectors or expressing vectors in different frames using rotation matrices, right? Because in this case, the 1 frame and the body frame, their origins are aligned. So I can directly apply a rotation matrix about the z-axis through the angle psi to get this red vector, right, that I'm looking for, expressed in either the body or the 1 frame, okay? So all I have to do right here is I need to have a rotation matrix which goes from the body frame to the 1 frame through the angle psi, right? So this is pretty simple, and in this case, this C1b over the angle psi, right? In this case, since we have a planar case, it's just a 2 by 2 matrix, right? And I think if you remember from our discussion, this is just cosine psi, sine psi, minus sine psi, cosine psi. Okay? Okay, great. Okay, so that's good for step 1. All right, how about step 2 then? Okay, what we want to now do with step 2 is we can actually go ahead and calculate the vector that we're kind of looking for. We're looking for T with respect to R expressed in the R frame, right? So let's look at that. So this is RT with respect to R expressed in the R frame, okay? So what is that? I'm looking for this green vector here expressed in your normal X, Y, or east-north coordinates, right? So again, if you just look at this picture from a vector mechanics standpoint, if we ignore what we are expressing, let me take off that subscript for a second, right? This green vector, just, go back to your intermediate high school calculus, right? Or geometry. I can't remember where we talk about all this in high school. But anyway, this green vector, it's just the vector sum of this plus this. Wouldn't you agree? So I can write this. It's the green vector is this first one, B with respect to R, plus RT with respect to B. Right? Can't argue with that. That's just a vector summation. The green arrow, you get it by adding these 2 red arrows together, right? Tip to tail, all that kind of good stuff. Okay, so now here's where it gets interesting. I want to express all this in the R frame, okay? Now, let's look at this. RB with respect to R. In order to get this expressed in the R frame, again, this better be in the R frame, right? Well, we already got that. That's measured by GPS, right? GPS is going to tell us how far east and how far north is the car with respect to the origin, okay? Now, this one right here, again, you need to have this in the R frame, right? In order to make this addition, and when you put in numbers and you actually want to carry out the calculation, you have to have them all in the same frame, okay? Now, what's interesting is if you think about this long enough, I'll just copy this again, plus, and again, let me get the vector, and then the subscript, we can be a little bit interestingly, and we can care about this here. Actually, I can write this. It doesn't have to be the R frame, it can be the 1 frame, right? And if you think about that long enough, hopefully you'll agree with me, because if you look at this, the 1 frame is exactly aligned with the R frame, right? So component-wise, the x components of the 1 frame will add directly to the x components of the y of the R. Sorry, make sure I said that right. The x components of the 1 frame will add directly to the x components of the R frame, and the y components of the 1 frame will add directly to the y components of the R frame, right? So actually, I can put in the superscript 1 here, right? It doesn't matter because these 2 frames are aligned. They are not rotated at all from one another. That's the beauty of it. Okay, great. And then in that case, you know what? Didn't we already calculate this right here? Okay, so let's just substitute this in. So we end up with, this is RB with respect to R in the R, plus Okay, let's substitute in our rotation matrix expression here. This is C1b over psi times R T B with expressed in the body frame. Great, and if you look at this, this is awesome because, again, the thing I want is on the left. We get this via GPS, I already have that. I can calculate this rotation matrix, no problem, if I'm given the rotation angle psi. Again, you know, this might come from like a magnetometer in this case. You know, a compass. All this thing is, it's the heading angle, right? It's the heading angle of the car. Remember, like going on top of this picture was our car sitting like that, and there's the angle psi. Whoops, I guess I obscured it a little bit. There's the angle psi, right? So it's just, you know, are you pointing northwest, southwest? How many degrees bearing is that, right? So I get this rotation matrix here. And then finally, this guy right here, RT with respect to B expressed in the body frame, that is what the car measured here via camera or LiDAR or what have you, right? Okay, so almost there. Let's just write this in matrix form, okay? If you look at this, what's over here on the left is, it's just a 2x1 vector, right? This thing is a 2x1 vector. So I can actually take this whole right side and I can write this in matrix form if we want. Let me go ahead and do that right now. Let me go ahead and write this as this. I'm going to do this, and then I want to pull out on this side RTB expressed in the body frame. Okay, and then a 1. Okay, so this RTB expressed in the body frame, that is what's multiplied with the rotation matrix. So I got to jam in this rotation matrix, C1b psi. And then what I can put here is we need to take this part into account, right? Multiplied by a 1. So this is just going to be RB with respect to R expressed in the R frame. Like that, right? Okay, and this gets us what we're looking for. This is RT with respect to R expressed in the 1 frame. Okay, now let's again be a little careful with dimensions here. Look at this over here. This is just going to be a 2x1 vector. What is this rotation matrix? This is a 2x2, right? This little guy here is a 2x2. This thing right here is a 2x1, right? So at the end of the day, this whole thing, right, is a, what? It's a 2x3 in this case. Okay, this thing here, what do we got here? This is a 2x2, just this vector, and then you have a 1x1. So this vector right here is a 3x1. So again, dimensions all line up, everything works well. The only small addition that I think we maybe might want to make right now is, I'm going to do this, and it might seem a little stupid, but bear with me. This is going to this is funny. Bear with me. This is going to bear fruit later on. But what we want to do is, let's do this. Let's go ahead and augment this left side. This might seem, again, a little silly, but all I'm going to do is I'm going to put a 1 down here. Okay, so this is a 1x1. Okay, so again, this whole thing over here becomes, and all I've done is I've added a 1 to the bottom. That means I need to add something on this bottom line here, which is going to read 1. So what I need to do is, again, I'm going to add 1 row to this matrix expression. Okay, so I'm going to go like this. Maybe let's put a little dot, 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 something like this. Okay. Oh, I need this bottom row to read 1 equals 1. So to do that, I need to jam in a 0 here and then a 1 to pick up this 1 here. And this 0 here, if you think about this from a dimension perspective, this is actually zeros. It's actually like 0, 0. So this is actually a vector of zeros of size 1/2, right? And this 1 right here, again, I better pick up this 1. So this is actually a 1/1, okay? So this entire matrix here is actually what? It's a 3x3 now, okay? And maybe just to kind of allude to why we're going to do this, because now this is nice, because if you think about it here, over here, the vector that's being operated on, it's a 3x1, and it kicks out another 3x1. This is gonna matter later on down the road when we want to do successive operations, okay? But tell you what, maybe I'm putting the cart in front of the horse right now. You know what? Let's call this vector over here, let's call it the pose of the system, okay? So sometimes people call this the pose. Let's go ahead and just call this, how about Pt with respect to R expressed in the R frame, or the pose. That's this 3x1. So this 3x1 over here, let's call this the pose of the system, but it's the pose of T with respect to B expressed in the body frame. Okay, and I guess we can put the vector notation there. Okay, and then let's call this 3 by 3 matrix here. Let's call this thing psi. Excuse my horrible notation here, but this is psi going from the body to the reference. You know, using our notation for rotation / transformation matrices, right? Now, okay, that's what we end up with, right? So this is just this, right? This 3 by 3 is this psi matrix, and then this is this. Okay, great. Okay, and you know what? If you look at this long enough, you see that this pose, it's really talking about the pose of this of the object of interest, or the system, right? It's the vector from the target to the body expressed in the body frame. You know what? There's extra B's here. This almost tells you too much information. It's fine to be more verbose, but what might make our lives a little bit easier is if we reduce this, and if we just drop this subscript notation here, because we're all talking about the position of the target, right? We all know that everything here is talking about the position of the target. And then same thing over here. This is target with respect to R expressed in the R. You know what? If I drop this subscript, you can almost have the same information. So we end up with, you know, you could rewrite this exact same thing as basically PR is equal to psi B with respect to R times PB. Okay? And this is nice, this formulation, because again, if you look at it, it looks very similar to our discussion of rotation matrices here, where you've got a vector expressed in some frame, and I'm going to now rotate it to express that same vector in another frame. The thing that's interesting about this is this psi matrix, right? If you look at it, it is the rotation matrix plus the translation. It takes both of these things into account at the same time. So this thing is not a rotation matrix by itself. It's a transformation matrix, right? It does rotation and translation at the same time, right? So that's what makes this thing so interesting. So yeah, I think we've got all of our definitions here. Why don't you give me a second to pause the camera, erase the board. Let's go through an example with actual numerical numbers and our situation up here. All right, so I've erased a lot of the board. I've kept our geometry and kind of the key transformation equation up, okay? Now, what we need to do is we need to start going around and filling in the stuff that we need to make this calculation. So, as we discussed, we need basically 3 things. I need to know the Euler angle for the rotation, and then I need these 2 vectors, okay? So let's just go ahead and do that. Let's first get psi, okay? So again, you know where psi is, right? Let's pull this car off, and so it doesn't obscure everything. Here's the angle psi, okay? Now, I want to make very careful calculations and measurements because, again, the geometry is going to matter. So let's go ahead and I'll drop on, I got myself a little protractor here cut out that I made. And let's go ahead and we're going to measure the angle between the x1 and the x body axis, and we see, I don't know, according to this, it looks like it's 40 degrees to me, okay? So it's a 40-degree right-handed rotation, okay? So psi in this example is 40 degrees, and again, I'm going to do everything in radians, so I have to multiply by pi over 180. Okay, great, we got that. Okay, let's pull off my protractor, don't need him anymore. The next thing we need to get is RB with respect to R expressed in the R. So again, this was the measurement made by GPS. So that is this red vector right here. I need this measurement, okay? So again, I want to be very precise with this. So what I'm gonna do is I'm gonna project that red vector down you know, as precisely as I can. So it's about here. Then I'll project it onto the Y reference, that's about here, okay? Those are our 2 marks, and then I'm actually going to physically measure them with a tape measure, okay? So I'm going to call that, that's 11.5 inches in the X, and then it is 9.75 in the Y. So let me see, sorry, what did I say? So this is 11.5 and 9.75, is that the numbers that we just made? Let me just double check that. I want to make sure that I get the number right because this is going to matter later on when we make our measurements. Okay, yeah, that's 11.5, and then this is Yep, 9.75. Yeah, okay, good, right? And again, this is because I want to express in the R frame. That's why I measured relative to frame FR, right? So here's how far you go in the XR direction. Here's how far you go in the YR direction, okay? Now, I need RT with respect to B expressed in the body frame. So again, this is going to be a 2-element vector, okay? But now, I need to get this red vector, but I need it expressed in the body frame, which is the blue set of axes, or I guess if you were looking at the car earlier, that it's supposed to be purple, but I didn't have a purple pen. But that's what I'm looking for. So what I need to do, we need to project this red vector into the blue set of axes. So I'm going to try to make a right angle as best I can here. I really wish I had. I mean, I guess this is probably as close as we're going to get. So it's about here. I guess this line should have been extended. Okay, it's about that far in the X, okay? And then I'm going to try to project this into the Y, and yikes, maybe I need to extend my Y axis a little bit. I should have had a square actually here, because now you can see where if you don't make the right measurement, the example can go wonky. Oops, and I'm using the wrong color. I want blue to kind of extend this axis. Okay, keep extending. Okay, something like that. Gosh, that's not even far enough, is it? No, that might make it. Okay. Okay, so square, it's kind of like, okay, I don't know. I think that's as best as I'm going to be able to get. Okay, so let's make these measurements now. So how far do I have to go in the X body axis to reach the point T? It is this distance here along my tape measure. It is 6 inches, okay? So let's write that down before we forget. So it's 6 inches in that direction. And then in the Y direction, we need to go this far, which is negative 9.5, right? So this one is negative 9.5 inches, okay? So this is negative 9.5. Okay, so with that, I think we've got enough to go ahead and make our calculations. So let's go ahead and compute our psi RB matrix, okay? So if you have this, we can take these two bits of information here, all right? And these are going to yield our psi B with respect to R, right? It's going to be our 3x3 matrix. Okay, so this first 2x2 quadrant was going to be our rotation matrix, right? So this was going to be cosine of, in our case, 40 times pi over 180, right? And then, what was it? Was it sine or negative sine? I got to make sure I don't get the SIGN of the SIN wrong. Where did I put this thing? Now I am. Did I actually get? Oh yikes! You know what? Hold on. We better be careful here. Let me rewrite what this is supposed to be. I'm worried on the board a couple of minutes ago. I wrote the opposite here. This is supposed to be. Yeah. Whoops. You know what? I had it right in my notes, and in my excitement, I think I wrote it backwards. I think I transposed this thing. So this is supposed to be cosine psi minus sine psi, sine psi, and then cosine psi. Yikes. So if I did, I'll have to, maybe, yeah, I'll tell you what, I'll fix it in the notes if I did it wrong. This is what it should be, okay? Should be cosine negative sine, sine cosine. That's what should go in here. So this should be negative sine of 40 times pi over 180, okay? And let's finish this guy off. So this should be positive sine, SIN, of 40 times pi over 180, and then cosine of 40 times pi over 180. Okay, great. That's this first entry. Okay, now this next 2x1 element is RB with respect to R expressed in the R, which we have over there. This should be 11.5 and 9.75. Great, and then finally down here in this bottom row, we got a 0 and a 0. That's this 1x2 set of zeros, and then I need a 1 here in the 3-3 element, okay? So great, here's psi R with respect to B, we already have the pose. So now let's generate from this vector right here, right? This will go ahead and we can make that into the pose expressed in the body frame, right? We said that the pose in the body frame, it's just a 3 by 1. The first two elements is just the position vector of t with respect to b expressed in the body frame, which is right here. So this is just 6 minus 9.5. And then we add a single scalar 1 in the bottom for this pose vector, okay? All right, so at this point, now to get the pose in the R, right, to get pose in the R frame, expressed in the R frame, it's just take your transformation matrix, psi b with respect to R, and multiply it by p with respect to b. So literally, it's just this matrix times this vector. So let's run over to MATLAB or Mathematica and have it just do that for us super quick. All right, so hopefully this is a pretty quick, easy calculation in Mathematica. So let's go ahead and define psi with xi, okay, and again, that's a nice, better version of my scribble on the board. So that's the symbol I was trying to scribble on the board for psi. Okay, so psi RB was our good old-fashioned 3 by 3 transformation matrix, which was cosine of the angle, which was, in our case, 40 degrees, times, what was it, minus sine of the angle, and then we had sine of the angle, and then cosine of the angle, right? So that was that first entry. The first 2 by 2 subblock, and then up here I think it was 11.5 and then 9.75, and then we had a 0, 0, 1. Okay, so there's our psi matrix, and then the next thing we needed was the pose PB. So again, that was our 3 by 1 vector of 6, what was it, minus 9.5, and then we needed a 1 at the very bottom, okay? So let's get those in, shift enter, and now let's just go ahead and calculate the pose of the system in the R frame, which was just going to be psi RB dotted with PB, okay? So let's go ahead and take a look at that thing in matrix form, and here's our answer, okay? So let's run over to the board and see if that checks out. All right, so we came up with the answer of the pose of the system expressed in the R frame was about 22.2, 6.3, and 1. Okay, so let's physically interpret what this meant. So if you remember, what the pose in the R frame, that PR, was our shorthand notation for this, which was really this vector, which was the position vector we care about, right? And then a 1 at the bottom. So really, this is the chunk of information that we care about in this first two elements. So what we have here is RT with respect to R expressed in the 1 frame is basically 22.2 and 6.3, right? And then remember, we said that this 1 frame and the R frame, since they were aligned, you can really switch this subscript to be an R. It's the same thing, right? So let's make sure that that is actually what we're trying to get, right? And let's dummy check and make sure this makes sense. So this right here should tell us where is the position of the pedestrian with respect to the origin of the reference frame expressed in the reference frame. So what that means is we need to go ahead and come back to our picture here, and let's take our position of the person, right, or the point T, and I need to project that into the R frame. So again, what that means is this needs to be projected down to about here, right? Okay, that's the X distance, and then the Y, let's project, again, it's this green vector, right? I need to get this green vector expressed into the Y frame, onto the Y axis. So again, that's something like, I think that's, geez, let's just call it around right there. Yikes. I think that's pretty good, right? So if we drew a straight line, I don't want to clutter up this diagram too much, but I think you get the point. Now, let's go ahead and actually physically measure this, make sure that that number we came up with jives. So this distance from the origin to that point is, look at that, 22.25. So to my imprecise measurements, this is 22.25. Right? Which sure lines up with this number. Like I'm actually amazed that that came out so well, given the impreciseness of how we measure the angles and all these distances. Let's try the Y and see if we got any better, right? It's how far is this distance? This distance here is about 6 and a little over 6.2. Oh my gosh. I cannot believe this. This is literally like 6.3 inches. I wish you could zoom in the camera to see that I'm not just pulling your leg, but that's literally it. This checks out. So look at this. Isn't this cool? So this psi matrix, this transformation matrix, it takes the rotation and the translation into account, and it's going to get you what you need. So this is pretty darn awesome. So if you think about it, again, from this self-driving car perspective, what we just did was we had the car driving along, you know, it left the base, right? It translated its frame away from the origin of the base frame, the reference frame. It drove around, and then it went and detected a pedestrian. It detected this target, right? Or this pedestrian that was using its own onboard sensor system, using, like, I don't know, camera or whatnot, and said, hey, look, I know that this person is a certain distance away from me, right? And it expressed that. I can't remember where we had that. Which one of those numbers was it? This guy, right? RT with respect to B and the B, right? It said it's 6 inches in front of me and 9.5 inches actually to my right, right? That's what it got, okay? So it measured that, and then we had GPS, which told us where the car was with respect to the base. So that was basically this red vector, right? RB with respect to R expressed in the R frame. And then we were, by measuring its heading, right, the angle between the two frames, we're able to create this transformation matrix. And then finally, now the base of operation knows where the target is without having to make a direct measurement of the target, right? We went through we went through this intermediate frame of the body frame to get to this position. So again, from the perspective, I think, of self-driving cars or automation, this is pretty darn cool, because now we can get that information without having to make a direct measurement, okay? Now, what I want to do is, let's talk about why did we add this silly little 1 at the bottom, this bottom row here, okay? So give me a second to pause the camera and erase the board, and let's think about trying to do this again, maybe. All right, so now that we've done this once, let's talk about how about composite slash successive transformations. What I mean by that is you can continue using this same idea over and over for different reference frames. So what I mean by that is, let's cook up a kind of a quasi-artificial example. Let's say, what if there was another car down here or something like that? Maybe I'll draw it, you know, like here's another car. I don't have another nice fun animation or cutout like this, but let's say you have another car. Let's say this car is kind of dumb, in the sense that it's not a self-driving car. It doesn't have all this onboard automation and all that kind of good stuff. But, you know, same thing. We can still go ahead and slap on a body frame to this dumb car, right? So here's X, maybe let's call it XD for X dumb, for the dumb car. And then again, I'll make a Y axis for the dumb car, like such. Y dumb car. Okay, great. So now we can almost do the exact same operation, and we can start asking ourselves, all right, is there now a vector from the origin of the dumb car to the reference frame? So yep, it's right here. Let me go ahead and draw that in red, like such. Okay. Okay, so now this is the position vector of the reference frame with respect to the dumb car, or FD, right? Okay, and now we could ask ourselves, what is the position vector? How is this car is not able to make a measurement or know anything about the target, but if we had successive information, if we were to send information down to it, could we calculate basically where is this pedestrian with respect to this dumb car? So again, I want this vector between the two, like such. Maybe I'll draw it with green, being the vector that we're kind of aiming for. So that vector, right? This is the position of the target with respect to frame D, right? Okay, so if you think about this again, it's basically another application of what we just did. All I need to know is I need to know the position of the dumb car with respect to the reference frame, and I need to now know the Euler angle of the rotation between the reference frame and the dumb frame here, right? So actually, you know what might actually almost be helpful is you can almost start thinking about this in the sense that, you know what? We already just calculated this vector, right? We know that this RTR with respect to this guy right here is known. Maybe I'll kind of put it in dashed, right? We just calculated this, Okay, so actually, you can start taking away this upper card. You can almost ignore all this junk up here, right? The calculation we just did, right? Because at the end of the day, all of that operation we just did basically got us this green vector. And now, this is just the exact same picture we saw earlier, right? So let's quickly go through the same operations of how we would go about doing this. Okay, so all we need to do now is I need to measure the angle between the dumb frame and the reference frame. So maybe what I should do is to maybe make that a little easier. Again, let's go ahead and I'll make an intermediate frame. Maybe I'll use blue again. Blue seems to be our nice intermediate frame color. I am going to superimpose that over here, and I want this to align, so maybe let's make it kind of like this. Yeah, that looks pretty closely aligned here, so I'll make this. Here's the X2 frame, and then again 90 degrees from that guy, like such. Okay, here's my Y2 frame. Okay, so now the Euler angle that I'm looking for is I want to look at how is the reference frame R rotated with respect to the D frame, but I'm going to use this intermediate 2 frame to do that. Okay, so you can see that here's one X, here's the other X that I'm looking for. So actually the Euler angle that I'm interested in this case is this angle all the way around. So from here to this, from the X2 all the way to the XR frame. Okay, this here's that angle. Let's call it theta just to distinguish it from psi. Okay, so that's the angle I need to measure. So let's go ahead and measure that right now. And unfortunately, my protractor only goes between 180 degrees. So tell you what, let's do the opposite measurement. Let's measure this interior angle like such. I'm going to overlay this here. Okay, that looks pretty good. Actually, it's got to be down a little bit like that. Okay, let's see. So that looks like negative 70 degrees. Okay, so this angle theta is about negative 70 times pi over 180. Or I guess if you want to take the 360 degree, the 360 minus this, what is that, 290? So it's 290 degrees or negative 70 degrees, however you want to think about it, that's totally fine, okay? And now, what else do I need to do? I need to now we need this vector. I need to figure out, so maybe we should do this again. We got theta here. We had said theta was minus 70 times pi over 180. Okay, now what I need is I need R with respect to D, right? I need this red vector, but I need this expressed in the D frame. Okay, so what I need to do is I need to get this red vector expressed in the D frame. So again, let's go ahead and project it onto the D frame. So maybe what we need to do is extend this D frame quite a ways, because it looks like it goes quite a ways. Whoopsies. Okay, something like that. Okay, so now I need to project the red vector onto the D frame. So let's do this. Let's get right angle like this. I think that's about as close to a right angle as I can get. Okay, so it's about there. Okay, and then I'm going to project it onto the Y axis. Also, I'm going to try to make this thing 90 degrees as much as I can. Okay, and then I'm going to project the red vector on. Let's call it about that. Okay. Okay, so now let's go whip out our tape measure. Where did it go? Okay, so how far do I need to go in the dumb frame to get to the origin of the R frame? So let's see, it's that distance. That looks like about 13 1/4 to me. So this guy is 13.25. And then how far in the Y? I go this distance, about 7.5. But again, look, it's in the opposite, it's in the negative YD. So this is actually negative 7.5. Okay, great. And then the last thing we needed was, I need this green one. I need RT with respect to R expressed, right? Let me write this down here. Where did I have that here? So we need RT with respect to R right? Which is what we just calculated, right? Expressed in the R frame, right? This was, what was it? It was 22 point, oh gosh, I forgot the exact number. We calculated it, but it was 22.2. Oh, actually, yeah, here, look, we measured it. That was our measurement. We said it was shockingly close to what we calculated. So 22.2, and then here, it was 6.3. Right? Okay, great. So with this, we can now basically do our calculation that we talked about earlier. I now need to get, I want R T with respect to D expressed in the D frame, right? This is what I want. So what we're going to do is we're going to, again, augment this thing with a 1 at the bottom. This is now going to be called the pose of the system. Let's call it pose expressed in the D frame, right? And then the same way we did earlier, we said, okay, the pose in the D frame is just going to be psi dr, right? And then I have the pose in the R frame, right? That's all we're going to do. So again, all we have to do is formulate this, guys. So again, we said our psi transformation matrix is our good old friend, our 3x3, where it's going to be cosine of, what is this, minus 70 times pi over 180. Geez, this is running out of space. I don't want to make this thing super ugly. Let's just call this cosine theta, right? Theta was up there, minus sine theta, cosine theta, right? Okay, and then 0, 0, 1. And then right here, what do we have? This guy was going to be our R dr with respect to D, so this is 13.25 and minus 7.5, okay? So that was our psi matrix times, what is the pose in the R frame? That is going to be 22.2 and 6.3 and a 1. Okay, so again, let's run over to Mathematica, go ahead and do this calculation. All right, so we're back at that same Mathematica notebook. Maybe what we should do is let's make a note that this first block of code was for our first transformation / rotation, and then let's go ahead and now start code for the second transformation. So again, let's go ahead and get our transformation matrix. That was psi dr, right? Which again was a 3x3 matrix, which looked a whole heck of a lot like the first one, except the only thing is that the angle has changed. So instead of being 40, it's now negative 70 degrees, right? So let's go ahead and update the angle for all of the rotation matrix portion. And then the translation, which was right here, this was now 13.25 and then negative 7.5, right? And now, notice this, we actually don't need PR, right? PR was already defined. We got that from the first transformation, so I don't actually need to input that. So now I can calculate PD, right? Which is just going to be psi dr dotted with PR, right? So let's go ahead and see what that comes up with. Okay. Let's go ahead and write this number down, jump back to the board to make sure that makes sense. All right, so we ended up here with the whole thing being, what, something like, it was about 26.8 and negative 26.2 and a 1. So this was the pose in the D frame. And again, what we care about here is these first two elements. These first two elements are going to give us the position of the target with respect to the D expressed in the D frame. So this is 26.8 and negative 26.2 inches in this case, okay? So again, this is what we got. Let's go ahead and make sure that this makes sense. This vector is supposed to be this super long green vector, right, which tells us where the pedestrian is with respect to the dumb car, but expressed in the dumb car's coordinate system, right? So what I need to do is let's project this green vector into the dumb car's coordinate system. So again, this is going to be a little bit, I apologize, we're going to probably gunk up and mess up this this board. Oh yikes, I'm really gonna have to extend this. Let's go ahead and extend this the x dumb axis pretty darn far. So x dumb goes like way up here, okay? Now I gotta take this green vector and I gotta project him. Let me move the dude. No, a right angle. I don't know, what does this look like? Is that kind of right angle-y? This is hard to see. I don't know, I'd give it something like that. I don't know, something like that. Okay, let's try that. Okay, and then I got to project it in the y direction. So yikes, I got to project the y dumb axis also pretty darn far. Something like that. Let's see if that's going to get us what we need. I'm going to go a right angle from the y dumb axis and up to that, guys. So that brings the green all the way down to it, somewhere in that neighborhood. Okay, so again, let's check this and see if this is in the realm of reasonableness. So the distance, how far you go in the x dumb direction to hit the pedestrian, right? Or I guess to avoid the pedestrian, hopefully, right? Is this distance, which is, let's measure this, 25-ish inches. So pretty darn close. And again, I think you can see why that didn't exactly check out. I'm making these horrible crude measurements, but it's in the realm of reasonableness, right? So that's perfectly good. And then same thing in the y-axis for the dumb frame. That's around, this is 27.25. So this is negative 27.25. So again, that number, man, checks out pretty darn close to that number. And again, you can easily excuse the small, minute errors, but the grand scheme of things, this seems pretty reasonable, right? So this is pretty darn cool. We were able to get PD, right? And now, this is where it gets interesting, and this is kind of why you see we added this one row of that effectively said 1 equals 1, because what this is allowing us to do, right, is if you back up, let's erase some of this, okay, and we'll start at the top, right? This basically is allowing us to make kind of these successive transformations. So right here, what do we have? We have the pose in the dumb frame is psi r to d times PR, pose in the R frame. Now, if you remember in the first calculation, right, didn't we calculate what PR was? That was just, again, a transformation matrix from the body to the reference, right? And then times pose in the body frame, right? So here, substitute this into this side, right? And you end up with psi dr times psi rb times pose in the body frame. This gives us pose in the dumb frame, right? So isn't this cool? Look at this. You can see how you start applying these successive transformation matrices. These psi matrices are basically going from one frame to another frame, and then again from that frame to a second frame, third frame, fourth frame, etc., right? So you can successively apply these transformations to get you measurements. We started, right? If you remember where we started, we had the vehicle out here, right? The vehicle was measuring the position to the target using its own interior set of sensors or what have you, right? So basically, let me do this in red. We started with this. So step one, start with this, right? Okay. Then what did we do? What we then did is we applied one transformation and rotation simultaneously via this psi matrix, right? That gave us this green vector, right? So again, I'm going to try to highlight, I guess I already highlighted it in black, but let's do everything in red. Let's solid red, how about? We'll circle everything as solid red, okay? So then, step two, what did we do? We said, okay, if you apply the first rotation / translation, right? That was all captured in this matrix psi b to r, right? That got us the position of the target with respect to r expressed in the R frame, right? And then after that point, we could throw away all that information about the car. Who cares? The end product was I got this green vector. Now we tacked on a second car, right? Or a second entity or a second frame, however you want to think about it. And we were able to calculate now this vector, this other green vector, right down here. So step then 3 was apply second rotation / transformation, right? And that was psi, what was that? That was from the R to the D frame, right? And that got us all the way down. So you can see how you can chain these together. If you have a bunch of measurements or you have a bunch of coordinate frames that are all set up one next to another, you can put them together successively using these psi matrices. And this is exactly why we wanted this thing. We had to have a row at the bottom to make this thing a 3 by 3, so that when you go ahead and successively keep adding and adding and adding and adding, it's fine. All the matrix multiplications work, the dimensions work out. So that's the one reason we kind of did this. It might appear superfluous line of the matrix, but it allows us to start tacking on these things and making successive operations, okay? And maybe a parting shot while we've got all this up, and I think it's pretty easy to see how we could do this, but I'm sure you're thinking, okay, you did all this in a planar sense, right? What about 3D? Well, this has a direct extension. I totally spelled that wrong. Extension to 3D, right? The base equation remains the same. You're still going to calculate the pose in, say, the D frame is going to be some transformation matrix psi times dr times a pose in the R frame, right? Okay. The only thing that's different now is that the sizes of these things change slightly. So now this psi matrix, okay, it's not going to be a 3 by 3, it's going to be a 4 by 4. Okay, and similarly, this pose, again, the pose is really simple. The pose is basically a vector and then a 1 at the bottom, okay? So all this is going to be, this is still going to be the position. Let me just make sure I'm getting this thing. I'm not quoting it or using the wrong subscripts. Where did I have that? Shoot. Yeah, come on, where did I put this down? PR. Long story short, this is R. This is R. This should be R, RD, right? Expressed in the D frame, I believe, was this vector, these first 3 elements, right? This is now the psi matrix. The psi matrix becomes this entire thing here, and then this here is the pose, the R. You still have the 1 at the bottom. Now, wait, sorry. Nope. I did have this backwards. This guy, hold on, let me write it like this. This is a 3 by 3. Okay. This is the position vector of R with respect to D expressed in the D frame. That goes in this far corner here, right? This 3 rows here at the last column. This one here is going to be RT with respect to R in the R frame, right? Okay, and then this 3 by 3 block, this is now going to be an entire, instead of just being, a single rotation matrix, you put in your entire direction cosine matrix or your DCM. It's a 3 by 3. Right? Which tells you how is the R frame rotated with respect to the D frame, right? That's what goes in there. And then still down here, you're going to have now a bunch of 0, 0, 0, 1, right? So again, it's just expanding the dimensions, and it's directly extensible to 3D, right? Let me just make sure I got this right. R, Yep, something like that, right? So it's directly extensible to 3D. So this is pretty darn cool that you could use this even if this car, came out of the plane, or if this was an aircraft, right, which was now maneuvering, excuse me, with respect to a base, or maybe it was like a robot or a robotic arm, which was moving with respect in 3 dimensions and 3 rotations and orientations with respect to some other frame. You still use this exact same framework. It's just your transformation matrix looks slightly different. So, with that being said, I think this is a great spot to leave it. I hope you enjoyed the discussion today, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll a little ways down and click on that subscribe button, it really does help me continue making these videos. We're about halfway through our discussion on some flight mechanics topics, so I hope you'll join us for one of these future videos. There's a playlist which contains all the flight mechanics videos in the description below, or in one of the pinned comments. Feel free to access it however you like. And with that being said, I really hope to catch you at one of these. So until then, I think I'll sign off for now. Talk to you later. Bye.